When you really look at the fundamental architecture of our digital world, the
Mhm.
code, the concepts, the whole infrastructure, it's kind of built on these pillars, you know.
Yeah.
And we often hear the same few names: Alan Turing, maybe John von Neumann, or Marvin Minsky.
And they are absolutely crucial, yes.
Hmm.
But if you were to point to just one person, one individual who simultaneously architected the field's philosophy,
Yeah.
created its main early language, and predicted its modern business model.
The whole multi-billion-dollar business model.
Exactly. That singular focus,
Yeah.
it really points to John McCarthy.
Right. And that's our mission today. We're going to do a deep dive into the life and, the monumental contributions of John McCarthy, American computer scientist, cognitive scientist, and one of the true, yet sometimes, overlooked intellectual giants of the 20th century.
He really was.
We want to pull out the core insights that show how one person managed to define three radically different but equally foundational areas of computer science.
It's an almost unbelievable trifecta of achievement. These are what we call his big three claims to fame, and they are, believe it or not, still shaping the technology you're using right now.
So, claim number one. Back in 1956, he officially coined the term artificial intelligence. He basically established AI as a formal field of study. He gave the future a name.
Then there's claim number two. He created the Lisp programming language, a technical masterpiece, really rooted in pure mathematics, which then went on to define the entire symbolic and functional programming paradigm.
And claim number three, and this is the one that touches every part of the modern internet. He was the main driver behind time-sharing. He popularized it. And that is the direct conceptual ancestor of modern cloud computing.
The utility model.
The whole thing.
That breadth is why he's so important. He didn't just contribute to a field that already existed. He was literally drawing the maps for multiple future fields. And to set the stage, you have to understand the academic world he was in. We're talking about high-stakes environments.
The absolute top tier.
McCarthy, who lived from 1927 to 2011, he graduated from Caltech, got his PhD in math from Princeton in '51, and then he proceeded to populate the most important intellectual hubs of computing history.
It's like a grand tour of innovation. He went from Dartmouth in 1955, which is where the AI story really kicks off, to MIT as a research fellow, and then finally to Stanford. He was a full professor there from 1962 all the way until he retired in 2000.
Right, and these were the intellectual battlegrounds where computer science was literally hammered into shape.
Yeah.
And his peers, his institutions, they all recognized the sheer scope of his influence. The awards he won really confirmed this dual status he had as both a brilliant engineer and a profound scientific theorist.
They were talking about the big ones.
The biggest. He received the Turing Award in 1971 for his work in AI, the prestigious Kyoto Prize in 1988, and the United States National Medal of Science in 1990. I mean, these aren't just lifetime achievement awards.
No.
They're a recognition that he laid the structural bedrock for almost everything that came after.
Okay, so to understand the architect, we have to understand the environment that shaped him. And his early life was, well, it was decidedly atypical for a figure who would later be seen as a pillar of Silicon Valley conservatism.
Oh, very much so. John McCarthy was born in Boston in 1927, and his heritage was really defined by the melting pot of that era. His father was an Irish immigrant, and his mother, a Lithuanian Jewish immigrant.
So that dual background was just the start of a childhood that was full of, well, intellectual rigor and some pretty intense politics.
It was. The family moved around a lot. They didn't really stay put. This was during the Great Depression, so they were constantly relocating until they finally settled in Los Angeles.
Why Los Angeles?
His father found stable work there as an organizer for the Amalgamated Clothing Workers Union.
Ah, a union organizer.
Exactly. And that move to L.A. coincided with a really deep political commitment. Both of his parents were active members of the Communist Party during the 1930s.
Which, looking back from today, it's a very specific political affiliation.
It is. But for the young McCarthy, what it really meant was growing up in an environment where debate, critical reading, rigorous analysis, questioning authority, all of that wasn't just allowed. It was actively encouraged. It was a fiercely intellectual upbringing, even if the ideology itself was controversial.
So his home life was basically a constant seminar. But the actual spark for science, that came from a pretty unexpected source, didn't it?
It did. His scientific curiosity wasn't sparked by, an American textbook. It came from a Russian popular science book for children called 100,000 Whys.
The Russian kids' book.
Yeah. The book was a collection of scientific facts, explanations, all presented in a really accessible way, and it It completely captivated him. And this wasn't just some brief fascination. It inspired him to become fluent in Russian later in life.
Which let him talk to scientists in the Soviet Union.
Exactly. He maintained these intellectual friendships even during the height of the Cold War.
And that curiosity, it quickly turned into some serious academic talent. I mean, he didn't just graduate high school early. He basically skipped the first 2 years of college math.
That's right. He taught himself advanced college-level mathematics. During his teens, he just studied the textbooks that were used at Caltech. So by the time he actually arrived on campus, he could immediately test out of all the foundational math courses.
That level of self-directed learning it's just incredible.
That's remarkable.
But for all that brilliance, he was still, a teenager.
Yeah.
And there's this deeply humanizing story. The future architect of AI was actually suspended from Caltech.
It's the great quirk in his record. And it wasn't for academic reasons. He was suspended for failure to attend physical education classes.
For skipping gym class.
Basically, yeah.
Yeah.
It was such a non-academic bureaucratic issue. He had to take a detour. He served briefly in the U.S. Army before being readmitted to finally get his Bachelor of Science in Math in 1948.
It's a great reminder that even geniuses have to, deal with the mundane rules of life. So when he finished his undergrad work, he went straight to Princeton for his PhD. Was the path to computation already set in stone for him, or was there another singular moment of inspiration?
The path was definitely solidifying, but there was one event. While he was still at Caltech, he attended a lecture given by the towering figure of modern computing, John von Neumann.
Oh, wow.
And von Neumann's lecture, which was all about the logical structure of computation and self-reproducing automata,
Yeah.
it was, by all accounts, electrifying. That was the experience that really cemented McCarthy's decision to move beyond pure math and dedicate his life to formalizing thought through machines.
Okay, let's circle back to his political roots for a second. You mentioned he was raised in this committed communist household, but he died a staunch conservative Republican. That ideological shift is fascinating.
It is, because it proves that the critical thinking skills his parents taught him ultimately trumped the specific ideology they held.
So it wasn't a rejection of their method, just their conclusion.
Exactly. His transformation was driven entirely by direct experience. I mean, despite his friendships and fluency in Russian, his visits to the Soviet bloc, particularly after witnessing the Soviet invasion of Czechoslovakia in 1968, that forced a profound reevaluation of his principles.
What was it specifically about the invasion of Czechoslovakia that catalyzed that shift?
Well, the invasion, which was known as the Prague Spring, was just this brutal suppression of a liberal reform movement. For someone like McCarthy, who valued intellectual freedom and rigor above all else,
To see that crushed.
to witness that raw authoritarianism, the denial of free expression, the huge gap between Soviet propaganda and the reality on the ground, it was intolerable to him. His shift wasn't a rejection of his parents' value of intellectual independence. It was the application of that very independence to empirical data.
So he looked at the evidence and changed his mind.
He did. He became a conservative because he believed the structures he observed in the West, especially around free markets and limited government, offered a more logical and a more robust path to freedom than the systems he'd witnessed firsthand behind the Iron Curtain.
And that commitment to logical rigor, regardless of where it led him politically, that translated directly into his professional life. And that leads us to his first monumental achievement, actually defining the discipline of artificial intelligence.
Right. The field needed a common banner. It needed a shared goal. Research into thinking machines had been floating around under different names: automata theory, cybernetics.
Kind of all over the place.
Exactly. But McCarthy and his colleagues, they knew they were doing something fundamentally different.
And that all culminated in the famous 1956 Dartmouth Summer Research Project on Artificial Intelligence. This wasn't just another conference. It was a watershed moment.
It was the formal establishment of the field. McCarthy co-authored the proposal for that project alongside giants like Martin Minsky, Nathaniel Rochester, and Claude E. Shannon.
And the objective they stated in that proposal, it was incredibly ambitious.
It was. They wrote that the goal was to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it.
And it's right there in the proposal, the naming ceremony. They needed a term to capture that ambitious goal.
And that term was artificial intelligence, or AI. By coining it, McCarthy really did two things. First, he gave the field a distinct identity, separating it from general computing or control theory.
And second?
He set a high but very clearly defined goal: the creation of intelligent artifacts.
What's so important here is that McCarthy didn't just stop at naming the field. He immediately started to define the logical structure that would be necessary to actually realize that name.
Absolutely. His 1958 proposal for the advice taker is a perfect example of this. Now, this wasn't a physical program yet. It was a conceptual design for an AI system based on logical principles.
So what would the advice taker do?
The idea was that it would process knowledge facts and rules given to it, and then use formal logical deduction to derive conclusions. So essentially, it would answer questions and plan actions based on the advice it had stored.
How was that different from how computers were being used at the time?
Well, at that time, computers were basically just number crunchers. They were designed to execute very specific, predefined algorithms for calculations like missile trajectories or accounting.
Right.
The advice taker, though, introduced this idea of representing knowledge symbolically and applying general logical inference rules to that knowledge. It suggested a machine that could reason, not just calculate. And that was the seminal concept that inspired all the later research in logic programming and sophisticated question-answering systems.
And an ambition like that immediately attracted the best minds. So you start to see collaboration, but also some intense intellectual competition shaping the field.
Oh, definitely. The early AI community was tiny, and that competition was formative. You had McCarthy, Minsky, Herbert Simon, Alan Newell. That was the core group.
So when Minsky, who is a key collaborator on the Dartmouth proposal, joined McCarthy at MIT in 1959.
The stage was set. It was set for some of the most intense, productive rivalry in academic history. They were racing, often against each other, to realize the promise of AI. And that competitive energy just fueled this exponential progress in the late 50s and 60s. So if naming AI was the theoretical foundation, that his second monumental contribution, the creation of the Lisp programming language, that was the indispensable toolkit. And we need to do a genuine deep dive here because the significance of Lisp is often misunderstood.
Okay, let's get technical. Lisp, which stands for list processing, was created in the late 1950s. Why did they need a completely new language? I mean, languages like Fortran were already emerging.
Because Fortran was designed for numerical computation, for crunching floating point numbers really fast. But AI needed to manipulate knowledge. And that meant manipulating abstract symbols and relationships.
Which Fortran just wasn't built for.
Not at all. McCarthy realized he couldn't do this efficiently using standard procedural logic. So his solution was revolutionary. He created Lisp by extending the mathematical concept of primitive recursive functions to operate on symbolic expressions, specifically on lists.
Okay, tell us more about primitive recursive functions. Why were they the jumping-off point?
Well, primitive recursive functions are at the core of computability theory. They're the simplest functions that computers can calculate. And McCarthy basically had this insight. He realized that if he could extend these fundamental functions to operate on lists of symbols, not just numbers, he could create a powerful, flexible structure for representing any kind of knowledge.
So anything from facts about the world to the rules of logic itself.
Exactly. And this brings us to that famous mathematical borrowing he introduced, lambda calculus. Now, that's a term that scares a lot of non-experts, but it's really the structural heart of Lisp.
It is the conceptual core, isn't it?
It is. Lambda calculus, which was developed by Alonzo Church, is a formal system in mathematical logic for expressing computation based on function abstraction and application. McCarthy borrowed the syntax of lambda calculus, specifically the lambda notation, to define how Lisp functions should work.
How can we visualize that for the listener? I mean, what does that mean practically?
Okay, think of it this way. In most traditional procedural languages, like early Fortran, a function is a rigid, step-by-step recipe for turning inputs into an output.
Right. A set of instructions.
Exactly. In lambda calculus, and therefore in Lisp, functions are treated as first-class citizens. They're almost like data. A function can be an argument to another function, or a function can return a new function as its output.
So it lets you build these incredibly flexible, self-referential structures. It's like being able to use a recipe as an ingredient in a new recipe, and then the result is a third, brand new recipe.
That is a perfect analogy. It's metaprogramming at its earliest and purest. And this design fundamentally changed the nature of programming. It defined the symbolic programming paradigm and became the immediate, indispensable language for virtually all early AI applications after it was published in 1960.
It's incredible.
And beyond that, every modern functional language, from Haskell to Scheme to Clojure, owes its philosophical and structural heritage directly to Lisp's foundation in lambda notation.
It's amazing to think that a language designed to solve these abstract problems of 1960s logic programming is directly responsible for shaping the programming style of, today.
But the creation of Lisp, with its radical flexibility and heavy use of dynamic memory, immediately created a massive practical engineering problem that McCarthy also had to solve.
And that was the invention of garbage collection.
That's right. This is a perfect example of a theoretical breakthrough forcing an engineering necessity.
So what was the problem that Lisp created?
Well, Lisp operates by constantly creating and destroying symbolic data structures in memory lots, trees, expressions. When a programmer is constantly creating new objects, the computer's memory quickly gets fragmented and cluttered with pieces of data that are no longer being referenced or used.
The garbage.
The garbage. And if you don't clean it up, the program runs out of memory and it crashes.
And this was traditionally managed manually by programmers, right? Which sounds tedious and very error-prone.
Precisely. Manual memory management is one of the biggest sources of bugs and instability in early programs. So around 1959, McCarthy invented methods for garbage collection, an automated memory management technique.
So instead of the programmer tracking everything,
The system does it for you. The system itself would periodically pause, identify all the unreferenced data structures, and then free up that memory for new use.
Wait, so the need to manage Lisp's complex structures led to the invention of a technique that is now fundamental to almost every high-level language we use today. Java, Python, C#.
It is entirely foundational. Garbage collection allows millions of developers today to focus purely on the application's logic, freeing them from the low-level, error-prone task of manual memory management.
So the pursuit of pure symbolic thought led to the solution for a fundamental infrastructure problem.
The irony is wonderful, isn't it? And beyond Lisp, we really shouldn't overlook his influence on general-purpose programming standards. He played a significant role in defining ALGOL 60, which was one of the most important early high-level languages.
He was on the committee for that, right?
A key member of the ACM committee. And his contributions there were absolutely transformative for general computing. Specifically, in August of 1959, he proposed incorporating two essential concepts, recursion and conditional expressions.
And why were recursion and conditional expressions so critical for ALGOL?
Well, recursion, the ability for a function to call itself, is absolutely necessary for elegantly solving problems that have naturally recursive structures like file systems or trees or certain mathematical patterns.
Before that, it was just messy loops.
Convoluted loops. By embedding recursion into LGL, McCarthy helped elevate the structural elegance and power of general-purpose languages. And conditional expressions, using if-then-else statements that return a value, also streamlined code, moving away from simple jump statements to more functional logical constructs. His participation here and later as a member of IFIP Working Group 2.1 ensured that his rigorous logical approach to language design got baked into international standards.
So we have the philosopher who named AI and the logician who invented functional programming and modern memory management. Now we shift from software and logic to physical infrastructure and economics. Part 4 covers his third monumental contribution, time sharing, which leads us directly to the modern cloud.
And this is where McCarthy's foresight becomes almost unsettlingly prophetic. He wasn't just thinking about how machines think. He was thinking about how people would access machines and how that access would be paid for.
Right, because in the early 1960s, a computer was this massive single-user machine. It cost millions of dollars. If you were a researcher, you had to book time, submit your punch cards, and then wait hours for the result.
Computing was a scarce, exclusive resource.
And time sharing was the radical answer to this scarcity.
It was. The idea was simple, but technically very complex. Instead of dedicating an entire mainframe to one user, the operating system would rapidly switch between processes, giving the illusion of simultaneous access to multiple users at separate terminals.
And McCarthy was instrumental in making this happen practically.
He helped create 3 of the earliest systems. The Compatible Time-Sharing System, or CTSS at MIT, the BBN Time-Sharing System, and the Dartmouth Time-Sharing System.
And time sharing wasn't just, an efficiency hack. It was a democratization of computing power. It allowed dozens of students or researchers to interact directly with the machine in real time.
It completely changed the workflow from batch processing to interactive computing.
Yeah.
And this technological leap, it led directly to his economic prophecy.
You're talking about the famous 1961 speech he gave at MIT's centennial celebration.
That's the one. He didn't just suggest time sharing was a good idea. He suggested it should be a business model.
A completely new one.
He suggested the concept of utility computing. This was maybe the first public proposal of its kind. He argued that computing power and specific applications should be sold through a utility model, just like electricity or water or gas.
So you'd plug in, use what you need, and get a bill based on your usage.
Exactly.
That is just staggering foresight.
Yeah.
To suggest that in 1961, when computers still used magnetic tape and punch cards, that computing would become a ubiquitous metered service that's visualizing an entire future economy.
It was wildly ambitious, and the initial idea really took off with great enthusiasm in the late 60s and early 70s. You had companies like GE offering time-sharing services. But then
a personal computer.
The rise of the cheap PC in the 80s made the idea of remote shared computing seem obsolete. Suddenly, people could own the resource locally.
But the pendulum swung back.
Dramatically. The internet explosion brought the concept roaring back, first as application service providers, or ASPs, then as grid computing, and finally, after 2000, as the massive infrastructure we now just call the cloud.
And if any listener needed that one single definitive takeaway connecting McCarthy to the modern day, this is it.
It comes directly from his colleague, Lester Ernest. He observed that the time-sharing systems they worked on in the 60s eventually came to be called servers. And Ernest noted, and now we call it cloud computing. That is still just time-sharing. John started it.
Wow.
It confirms that every time you use Amazon Web Services or Google Cloud or Microsoft Azure, you are using the economic and technical framework that John McCarthy conceptualized 6 decades ago.
And beyond just the technology, the man also understood that big ideas need big institutions to nurture them. His role in institution building was just as crucial as his inventions.
He was a driving force. At MIT, his efforts helped motivate the creation of Project MC, which became the cornerstone of MIT's computer science and AI research.
And when he moved to Stanford, he did it again.
He replicated that success. He helped establish the Stanford AI Laboratory, or SAIL.
And these weren't just parallel labs, right? They were intentionally friendly rivals.
Exactly. SAIL was, for many years, the primary friendly rival to MIT's Project MC. And this competition was essential. It spurred innovation, it attracted the brightest students, and it created the academic infrastructure necessary to push the boundaries of AI and computing through the 60s and 70s.
So the whole field benefited.
The entire field benefited. And just to show that the early drive wasn't purely academic, you can look at the famous Kotok-McCarthy match.
A chess match against the Soviets.
In 1966, yes. McCarthy's team, representing the U.S., used a program they wrote to play a series of chess games against their Soviet counterparts. They ended up losing 2 and drawing 2, so it wasn't a victory. But it demonstrated that early practical drive for application. It was an intellectual Cold War battle waged on a chessboard, proving that symbolic programming could tackle complex, real-world strategic problems.
Okay, so we've covered his contributions to naming, to programming, and to infrastructure. Now we need to explore what he really truly cared about. The philosophical implications of AI and the fierce intellectual debates his logic-based optimism inspired.
Right. At his core, McCarthy was a profoundly committed artificial intelligence optimist. He never wavered in his conviction that human intelligence, all of it, could eventually be formalized precisely enough to be programmed into a machine.
So to him, the human mind was complex, but fundamentally computable.
Yes, and this optimism led him to develop formal logic systems that were designed explicitly to capture the messiness of human thought.
His most important work in this area was his development of circumscription, right, between 1978 and 1986.
That's right. Circumscription is a method of non-monotonic reasoning, and that's a crucial distinction. Traditional logic is monotonic. If you add a new piece of information, you never retract an old conclusion. It only grows.
But that's not how human reasoning works at all. We constantly change our minds when new facts contradict our old assumptions.
Precisely. If I tell you birds can fly, you conclude that Tweety the canary can fly. But if I then tell you Tweety is a statue, you retract the initial conclusion. That is non-monotonic reasoning. It's the ability to change your mind when you're presented with contradictory, but more specific, information. Circumscription was McCarthy's attempt to formally model that crucial, everyday human ability.
He also worked on something called situation calculus. What was that focused on?
Situation calculus was another formal logic, and it was designed to represent and reason about dynamic situations and changes in the world. It's a language for describing actions, their preconditions, and their resulting effects. Both of these were part of his lifelong campaign to formalize common sense.
That vast, often implicit body of knowledge that lets us navigate the world.
Exactly.
And this confidence in logic led to one of his most famously provocative statements, a thermostat test.
In his 1979 article, Ascribing Mental Qualities to Machines, McCarthy deliberately pushed the boundaries of what intelligence meant. He stated that, and I quote, "Machines as simple as thermostats can be said to have beliefs."
A thermostat has beliefs.
His argument was that if a device performs a problem-solving function, the thermostat believes the room is too cold and therefore it turns on the furnace. We can functionally ascribe beliefs to it, even if those beliefs are very simple. He was equating a functional behavior with a mental state.
But that philosophical position immediately triggered the biggest counterpunch in the history of AI philosophy.
It triggered John Searle's famous 1980 response, the Chinese room argument.
Right.
Searle argued that merely manipulating symbols according to rules, which is what the thermostat, or even a sophisticated AI does, is not the same as true understanding or intentionality. The machine lacks consciousness. Searle's thought experiment showed a person in a room manipulating Chinese characters based on a rule book, successfully communicating without understanding a single character of Chinese.
So the core tension was, McCarthy was a functionalist, arguing that if it behaves intelligently, it is intelligent. And Searle was an intentionalist, arguing that behavior without genuine consciousness is just simulation.
That tension, functionality versus intentionality, it generated a massive amount of literature, and it remains the defining philosophical boundary dispute in the field. McCarthy was challenging us to expand our definition of belief. Searle was defending the uniqueness of human experience and consciousness.
And the conflict wasn't just with Searle. McCarthy had a long, defining professional debate with Hubert Dreyfus, the philosophy professor at Berkeley.
Oh, yes. Dreyfus was perhaps the most famous and persistent skeptic of early logic-based AI. He fundamentally disagreed with the idea that human reasoning could be reduced to formal, logical systems. Dreyfus, who was influenced by existentialist phenomenology, saw human understanding, especially expertise and intuition, as being deeply embedded in the body, in experience, and in contextual understanding that just transcends explicit rules.
It sounds like Dreyfus was arguing that you can't program wisdom.
Essentially, yes. He viewed the human experience as encompassing these deeper existential questions about the good life, about meaning, about choice. And he argued that these dimensions of reality and intuition could never be reduced to a symbolic calculus. For McCarthy, the challenge was just a matter of technical complexity. The formalization was possible, just difficult. For Dreyfus, the challenge was fundamental and philosophical. They represented the two irreconcilable poles of the AI debate for decades.
And despite all this intense skepticism, McCarthy never backed down from his optimism. He always held firm to the ultimate computability of the mind.
He was unshakable. He addressed the skepticism about spiritual or transcendent intuition in a 1989 interview. He said that the view that such things are not physically accessible has been in steady decline for centuries, ever since the scientific revolution started chipping away at supernatural explanations. McCarthy fully expected that the difficult challenge of realizing human consciousness in machines would eventually be overcome through logical formalization and engineering ingenuity. He saw no magical barrier, only a temporary technical one.
McCarthy's sheer intellectual range extended far beyond, logic gates and programming languages. Before we conclude, we have to look at some of his more unique later work, including an idea for literal space travel infrastructure.
The space fountain. This concept, which he proposed around 1982, it just showcases that McCarthy never lost that childhood interest in grand engineering problems.
I always found this idea so compellingly strange. How was this massive tower supposed to function without traditional structural support?
Well, it was conceived as a non-rocket space launch system, a tower extending hundreds of kilometers into space. But unlike a traditional space elevator, it wouldn't rely on tensile strength. Instead, it would be held vertical by a stream of small, high-velocity pellets propelled continuously upward from Earth.
So the momentum of the pellets keeps it up.
The outward momentum of that stream, constantly resupplied, would keep the structure rigid and vertical.
And the payloads, how do they get up?
Payloads would ride a separate parallel conveyor built up the inside of the structure, using the constant momentum of the pellet stream as its support and stabilization. Then the pellets would be returned to Earth to repeat the whole process.
That's wild. It's a remarkable combination of physics, engineering, and just pure imagination.
And he also embraced the early dawn of digital culture in a way that really bridged the academic and the everyday.
He was active on Usenet.
Very active. He was a participant in Usenet forums, which was the original social networking ecosystem of the academic world. He frequently commented on world affairs and engaged in spirited intellectual exchange. He was also a devoted book reader, actively attending SF Bay Area dinners for RAB readers-rec.arts.books, the famous RAB fests.
And that presence in early digital culture gave us one of his most famous personal tenets, which served as his Usenet signature.
It was his mantra, his belief in the importance of grounding opinions in quantifiable fact. He who refuses to do arithmetic is doomed to talk nonsense.
He even had it on his license plate cover.
He did. And that quote just perfectly encapsulates his lifelong belief in mathematics education, critical thinking, and logical rigor as essential prerequisites for sound political and social discourse.
He was also a staunch defender of controversial speech, wasn't he? Which reflects that early commitment to critical thinking, even when it caused friction at Stanford.
Yes, in 1989, he actively defended controversial free speech, even involving European ethnic jokes at Stanford. His position wasn't an endorsement of the content of the jokes, but a principled stand. He believed that in the pursuit of intellectual and political honesty, one must tolerate speech that is offensive as long as it's part of a necessary, rigorous intellectual exchange. He was consistent. Freedom of thought requires freedom of expression.
His final years also saw him turn his philosophical questions into fiction, which is a wonderful full circle for a scientist.
His 2001 short story, The Robot and the Baby, used a fictional scenario to explore those central philosophical challenges of AI specifically, whether robots should truly have emotions or merely simulate them. It was a farcical but really insightful look at the very questions that had defined his rivalry with Searle and Dreyfus, and it anticipated many of the cultural concerns we have today about AI transparency and social interaction.
And on the professional side, his legacy of mentorship is also crucial. He didn't just invent, he trained the next generation.
He advised 30 PhD graduates, including computing luminaries who would go on to shape the field themselves. People like Barbara Liskov, who won the Turing Award in 2008, and Raj Reddy, another Turing Award winner. That is an enormous influence. It's like extending his intellectual DNA across the entire industry.
And while his complex personal life included tragedy, his second wife, Vera Watson, who was a programmer and a dedicated mountaineer, tragically died attempting to scale Annapurna Central in 1978. His professional contribution remained a constant, powerful force.
And his recognition was sustained right up until his death in 2011. He was inducted as a Fellow of the Computer History Museum in 1999, specifically for co-founding AI and time-sharing, and he was posthumously named a 2012 Stanford Engineering Hero. His body of work remains arguably the most comprehensive and multifaceted in the history of computer science.
You know, looking back over this deep dive, we realize that John McCarthy wasn't just a participant in the computer revolution. He was an explosive polymath who defined its essential ingredients. He gave the field its name, provided the logic framework that defined symbolic computation through Lisp,
And functional programming.
and then, decades early, drew the economic map for utility computing, which is now the cloud. His whole career was just this relentless application of logic and a profound optimism about the power of formal systems.
And that optimism is the key takeaway for you. McCarthy fundamentally believed that knowledge, even the most elusive forms of human intelligence, could eventually be formalized and programmed. He solved massive formalization challenges in symbolic logic and in infrastructure.
But the challenge he set for himself, to realize human consciousness in machines, that is still the defining struggle for AI today. We live in the technological world he predicted, but we are still striving to build the reasoning machine he envisioned.
So we connect this back to the frontier. If the infrastructural challenge was solved by time sharing becoming the cloud, and the symbolic challenge was solved by Lisp and functional programming, what is the next unformalized, common-sense challenge that today's AI architects need to conquer? I mean, McCarthy was working on things like elaboration tolerance, the ability to deal gracefully with vast quantities of facts without explicit guidance, and the formalization of context.
Which leads to our final provocative thought for you to chew on. If John McCarthy proved that symbolic thought could be structured logically, what fundamental human characteristic, beyond mere consciousness or intuition, remains the ultimate programming challenge for today's AI? What's the next thing that must be formalized before a machine can truly possess common sense and wisdom, rather than just impressive processing power? That, in a very real sense, is the map that McCarthy drew for us to follow.